Leather processing and cleaner production approaches, a chemical perspective. The leather processing industry plays a significant role in global economic development by converting byproducts of the meat industry, raw hides and skins, into durable and stable materials known as leather. Leather manufacturing involves a sequence of chemical reactions and mechanical treatments that stabilize the collagen matrix of animal skin, producing a material that resists microbial degradation, mechanical wear, and environmental stress. Conventional leather processing requires more than 130 different chemicals throughout the production cycle. These chemicals facilitate preservation, cleaning, depilation, tanning, and finishing processes. Despite its economic importance, the leather industry is widely recognized as one of the most polluting industrial sectors. Tanneries discharge substantial quantities of solid, liquid, and gaseous wastes into the environment. Approximately 75 to 80% of the original weight of raw hides and skins becomes waste during processing. Solid wastes include fleshing residues, trimming scraps, hair, wool, shavings, buffing dust, and splitting waste. In addition to solid waste, medium-sized tanneries may discharge over 300 cubic meters of wastewater per day, containing large concentrations of pollutants such as chemical oxygen demand, COD, biological oxygen demand, BOD, nitrogen compounds, suspended solids, SS, sulfate and sulfide species, total dissolved solids, TDS, chromium compounds. These contaminants can significantly affect surface water, groundwater, soil fertility, and ecosystems. Tanneries also release hazardous gases such as hydrogen sulfide, H2S, ammonia, NH3, and particulate dust, posing risks to human health and the environment. Growing environmental awareness and regulatory pressure have encouraged the development of cleaner leather production technologies. These approaches aim to reduce chemical consumption, minimize pollution, and improve sustainability while maintaining leather quality. Overview of leather processing. Leather processing typically consists of four major stages: preservation of raw hides and skins, beamhouse operations, tan yard, tanning operations, post-tanning and finishing processes. The most chemically intensive stages are beamhouse operations and tanning, where large amounts of chemicals and water are consumed. Cleaner production strategies focus on eco-friendly raw materials, enzyme-based processing, recycling of wastes and chemicals, reduction of toxic reagents, development of alternative tanning agents. Preservation of raw hides and skins. Freshly flayed hides and skins are highly susceptible to microbial degradation because they contain proteins, fats, and moisture. To prevent decomposition before processing, hides must undergo curing, which is a preservation method used during storage and transportation. Conventional salt curing. The most common curing technique uses 40 to 50% sodium chloride. Salt draws moisture from the skin and inhibits microbial growth. However, this method contributes significantly to environmental pollution. Major environmental problems associated with salt curing include high total suspended solids, TSS, increased TDS, up to 70%, elevated COD and BOD, release of chloride ions into wastewater. Excess chloride contaminates soil and water resources and is difficult to remove from tannery effluent. Cleaner preservation methods. To reduce salt pollution, researchers have investigated several alternative preservation strategies. Chemical alternatives. Salt substitutes include soda ash, potassium chloride, silica gel, boric acid, polyethylene glycol, PEG. Biocides such as terramycin and aureomycin have also been used to suppress microbial growth. Physical methods. Physical preservation techniques include controlled drying, sun drying, chilling with cold air or ice, carbon dioxide dry ice preservation, irradiation treatment. However, drying methods must be carefully controlled because excessive dehydration can cause fiber coalescence and cracking in the skin structure. Plant-based preservation. Natural extracts from various plants have also been explored as antimicrobial curing agents. These approaches reduce salt consumption but rarely eliminate it. Their effectiveness may depend on the bacterial species present on the hides. Overall, cleaner curing technologies focus on salt-free or low-salt preservation, plant extracts, and synthetic biodegradable preservatives. Cleaner options in beamhouse operations. Beamhouse operations prepare the hide for tanning by removing impurities, hair, fats, and non-collagenous materials. Major steps include soaking, liming and dehairing, fleshing, delimbing, baiting, pickling. Each step has environmental implications. Soaking. Soaking is the first chemical operation in leather processing. Its main objectives are rehydration of cured hides, removal of dirt, blood, and dung, elimination of soluble proteins and preservatives. Conventional soaking uses soda ash, surfactants, biocides, and residual salt, resulting in significant wastewater contamination. Typical pollution loads include cod, 22 to 33 kilograms per ton of hides. BOD, 7 to 11 kilograms per ton. TDS, 85 to 113 kilograms per ton. Cleaner approaches. Enzyme-assisted soaking has been proposed as a greener alternative. For example, alkaline protease enzymes can reduce water consumption by about 66%, decrease soaking time by 50%, eliminate the need for baiting, reduce chemical dehairing agents by 50 to 60%. Enzymatic soaking enhances processing efficiency while lowering environmental impact. Liming and dehairing. Liming is a critical step in leather production that removes hair and non-collagenous proteins while swelling the hide to facilitate fiber separation. Conventional liming uses strongly alkaline solutions, pH 12.5 to 13, containing calcium hydroxide, lime, sodium sulfide, sodium hydrosulfide. These chemicals dissolve hair and fats, producing wastewater with extremely high BOD, cod, sulfide, and TDS concentrations. Liming operations account for 60 to 70% of the total pollution load from tanneries. Hydrogen sulfide gas produced during this stage is highly toxic and contributes to air pollution and acid rain. Cleaner alternatives. Several greener methods have been developed. Enzymatic unhairing. Proteolytic enzymes from microorganisms such as bacillus species can loosen hair without dissolving it. Hair can then be removed mechanically, reducing organic pollution by approximately 60%. Hair-saving methods. Techniques such as the painting method remove hair intact rather than dissolving it. These methods reduce water consumption by 40 to 70% and decrease sulfide usage. Nanotechnology-based enzymes. Immobilized enzyme systems using nanoparticles have also been developed. Enzyme cocktails attached to iron oxide nanoparticles can remove hair effectively within about 7 hours while preserving collagen integrity. Fleshing. Fleshing is a mechanical process that removes residual fatty and connective tissues from the hide using fleshing machines. Traditional fleshing generates large quantities of waste containing lime residues, 2 to 6%, fats, 4 to 18%, proteins, 5 to 7%. These wastes produce greenhouse gases such as CO2, NH3, and H2S when decomposed. Cleaner strategies. Cleaner technologies emphasize waste recycling and reuse. Fleshing waste can be converted into valuable products, including soap, biogas, fertilizers, gelatin, glue, activated carbon, fat liquoring agents. Such recycling approaches transform waste into useful materials and reduce environmental pollution. Delimbing. Delimbing neutralizes the high alkalinity introduced during liming and lowers the pH to approximately 8 to 9. This step removes calcium compounds and prepares the hide for enzymatic baiting. Conventional delimbing uses ammonium salts, particularly ammonium sulfate, ammonium chloride. These chemicals generate wastewater containing 2,000 to 4,000 milligrams per liter ammonia nitrogen, NH3N, which contributes to eutrophication and oxygen depletion in aquatic environments. Ammonium-free delimbing. Cleaner alternatives include carbon dioxide, organic acids, formic, lactic, citric, glycolic acid, boric acid, gluconic acid, EDTA-based chelating agents. Carbon dioxide delimbing is widely studied because dissolved CO2 forms carbonic acid, which neutralizes lime. However, it requires specialized equipment. Other organic acids may cause excessive pH reduction or slow penetration, which can affect leather quality. Baiting. Baiting is an enzymatic treatment that further removes interfibrillary proteins and opens the collagen fiber network. Common enzymes include trypsin, microbial proteases, keratinases. Baiting improves the softness, pliability, and cleanliness of hides before tanning. Because enzyme concentrations are relatively low, this step generally has minimal environmental impact compared with other Beamhouse operations. Pickling. Pickling prepares the hide for tanning by lowering the pH to 2.5 to 3 using acids and salts. Typical pickling formulations include sulfuric acid, hydrochloric acid, formic acid, sodium chloride, 6 to 8%. Salt prevents excessive acid swelling of collagen fibers. However, large quantities of chloride ions increase TDS levels in wastewater. Cleaner pickling methods. Two major strategies have been proposed: salt-free pickling using non-swelling acids such as sulfonic acids. Recycling of pickling liquors to reduce wastewater discharge. Sulfonic acids also improve chromium uptake in subsequent tanning processes. Tanning operations. Tanning converts raw hides into leather by stabilizing collagen against heat, moisture, and microbial degradation. Tanning agents form cross-links with collagen fibers, increasing mechanical strength and resistance to decomposition. Traditional tanning agents include chromium salts, aluminum salts, zirconium salts, vegetable tannins, aldehydes, oils. Currently, chrome tanning dominates the leather industry, accounting for nearly 90% of production because it provides excellent strength, flexibility, and hydrothermal stability. However, chromium tanning releases large quantities of chromium into wastewater. Oxidation can convert trivalent chromium, Cr3+, to toxic hexavalent chromium, Cr6+. Cleaner tanning technologies. Cleaner tanning approaches focus on three main strategies: chrome-free tanning agents, improved chromium utilization, chromium recovery and recycling. Vegetable tanning. Vegetable tanning uses polyphenolic compounds extracted from plants, such as wattle, chestnut, quebracho, myrobalan, tara. These tannins have molecular weights between 500 and 3000 daltons and contain hydroxyl and carboxyl groups that cross-link with collagen. Vegetable tanning consumes approximately 350,000 to 400,000 tons of tannins annually worldwide. Advantages include renewable raw materials, reduced heavy metal pollution. However, vegetable tanning also has limitations: longer processing time, high organic load in effluents, color changes due to photooxidation. Combination tanning methods using vegetable tannins with aluminum or glutaraldehyde improve leather properties and reduce pollution. Alternative mineral tanning. Other mineral tanning agents being studied include aluminum salts, zirconium salts, titanium salts. Zirconium tanning shows promising properties but may cause uneven distribution due to high reactivity with collagen. Aluminum tanning produces white leather with good softness but limited thermal stability, approximately 75 degrees Celsius. Combination tanning systems are therefore often used to enhance performance. Nanotechnology in tanning. Nanotechnology has recently emerged as an innovative solution in leather processing. Nanoparticles can penetrate collagen fibers easily and enhance tanning efficiency. Benefits include increased chrome uptake, reduced chromium discharge, improved mechanical and thermal properties. Nanomaterial-based tanning can also introduce additional functionalities such as antimicrobial activity, UV resistance, fire resistance, self-cleaning properties. Polymer-based tanning agents. Hyperbranched polymers and synthetic polymeric tanning agents have also been developed as chrome-free alternatives. These polymers contain numerous functional groups capable of forming strong interactions with collagen fibers. As a result, they improve tensile strength, softness, mechanical performance. Polymer nanoparticle composites, such as vinyl polymer, ZNO nanocomposites, have also shown promising results. Comparison of conventional and cleaner technologies. Time. Cleaner technologies may require longer processing times in some cases, particularly for vegetable tanning. However, enzyme-assisted methods and nanotechnology can reduce processing time in certain steps. Cost. Cleaner technologies are often more economical because they utilize locally available biological materials and reduce chemical consumption. Product quality. Traditional chrome tanning generally produces leather with superior mechanical properties. Cleaner methods can produce comparable quality but often require optimization or combination techniques. Conclusion and future perspectives. Leather processing remains one of the oldest and most important industrial sectors worldwide. However, the conventional processes involve large quantities of water, energy, and hazardous chemicals, resulting in severe environmental pollution. Cleaner leather production technologies aim to reduce these impacts through enzyme-assisted processing, plant-based chemicals, waste recycling and reuse, alternative tanning agents, nanotechnology and polymer-based systems. Although many cleaner alternatives have been developed, most still do not fully match the performance and versatility of traditional chrome tanning. Continued research is therefore necessary to improve environmentally friendly processes while maintaining high leather quality. Future advancements are expected to focus on biotechnology, nanotechnology, and sustainable chemical systems, enabling the leather industry to transition toward greener and more efficient production methods.